opposing magnetic field that exactly cancel moving magnetic. So moving magnetic field this way creates a magnetic field in the opposite direction that exactly cancels that motion. So ideally what you'd have is you drop it in and it would just float there. And this is what we want to work towards, is getting something that floats. That's cool. The reason in this case that it does it is copper is a good conductor. It's a very good conductor. It's one of the best ones we have in room temperature, but it's not the perfect conductor. It doesn't have zero resistance. You run an ohmmeter there, you'll measure a resistance. So what's happening is we drop the magnet, we suddenly get these currents circulating, creating a magnetic field, but at the same time these currents are bouncing off defects and other atoms, the copper atoms that are there, bouncing off the sides, and it's creating heat. So you're creating a magnetic field, you're also creating heat as it falls. And that heat is what's keeping that thing from just floating there. And so it's useful for generating electricity, but this heat that we create is also not so good because it draws power away. So that's why power generation is not 100% efficient. We have these part of the reasons we have these resistive losses in the coils of wire. We have resistive losses in this copper pipe, and that's because everything has a resistance. In opposition to motion of electrons, I guess. Now there's some tricks we can play. If we want to get this thing to levitate, we can take this copper block and cool it down. So what happens with metals is, I mean, normally you talk about, okay, Ohm's law, V is equal to I times R. R is a constant for the material. It's not, actually. R is it can vary with temperature, for instance. That's one thing you can vary. You can also vary with pressure and other things, but temperature is definitely the easiest one to control. If we heat up a piece of metal, the resistance goes up. If we cool down a piece of metal, the resistance goes down. And this actually only works for metals. Semiconductors work exactly the opposite way. For a semiconductor like silicon, like what's in your computer, you heat your computer up, resistance goes, you heat your computer up, resistance goes down. You cool your computer down, resistance actually goes up. Now there's limits to that. People cool down their computers all the time, but that's because they're doing something a little different. You're not actually cooling it down to decrease the resistance, you're cooling it down to get the heat away from it so it doesn't catch fire. That's the difference. That's what those weirdos who burn their computers all the time do. So that's what I wanted to do. That's the easiest way to change the resistance. So you see this here. And what I have here is it's the same type of rare earth magnet I was using before to drop through the pipe. This time it's just a different shape. And I would demonstrate that it's exactly the same, but it doesn't quite fit through the pipe, unfortunately. I suppose I should get a bigger pipe. But what I'll do here instead is I'm going to take this magnet and I'm going to drop it, first of all, on top of the ground here. Let's see what happens. So I have my fingers in the magnet. So you can see it falls quickly and starts jarring around, it bounces around a little bit. This isn't conducting, it's foam, so it's not going to do very much. You can't really get current to move through foam, and you can't get the opposing magnetic field. Now I'm going to do it on top of a block of copper, and based on what we just saw, what we expect to see here is that it's going to fall slower. And that actually is, maybe if you watch that, it's easy to see. So you can see here, it falls a little faster and you get all this bouncing around. Here, we put it on top of a copper block. Let it fall. It falls a little bit slower. And actually, if you have a magnet like this and a block of copper, you should actually try it. Try moving it around on top of this. You'll actually feel that something's pushing back at you as you get closer and closer to this block. It's a really neat thing to try. Just drop it, and it falls slower. Okay, so that's at room temperature resistance. The next thing I want to do is I want to really lower the resistance, and I can cool it down in increments with regular cryogenic techniques and put it in the fridge or something. But we want to go all the way. We don't want to do an experiment here. We don't want to control the variable slowly. We just want to show you what's going to happen. So what I have here is liquid nitrogen. This is about as cold as I want to go in terms of the amount of cost that we're going to get to. Liquid nitrogen is cold. Liquid nitrogen is 77 Kelvin and minus 196 degrees Celsius. So minus 196 degrees Celsius. So nitrogen makes up 70% of our atmosphere. This is it cooled down so low that it's gone through a phase transition, it's now a liquid. And it boils at 77 Kelvin. So I'm going to take that stuff, I'm going to pour it in here and then cool down this copper block. And eventually it's going to get down to 77 Kelvin and we're going to have a cold piece of copper. Hopefully with lower resistance. This will take a few minutes though, so in the meantime, I want to show you some of the neat things you can do with cryogenic liquids. And some of the neat things that come out of playing with them. So like I said, the first thing, maybe you can see that there. Yeah. You see how it's boiling like mad right now? What's happening actually is as the amount of nitrogen lowers, what we're going to start seeing happening is that little bits of nitrogen are going to get on top of that, and it's going to skimmer around on top of that flat surface, the same way that water does on a hot plate or on a stove. And what's happening here, it's actually called a leading frost effect. There you can probably see it. You can see little bits of nitrogen boiling over the top and just skittering across the top. What's happening, it's called the leading frost effect. And basically the same thing that happens with the water. If you have a surface that's well above the boiling temperature, or a surface that's heated up to above the boiling temperature of the liquid you're putting in there, or anything you're putting in there actually, that liquid hits the surface, and suddenly the part that just touched it, there's no time for the heat to conduct to the rest of the material. It hits it, it explodes into vapor, and you have, in this case, your nitrogen, or your water if you're using your stove or hot plate, floating around like a hovercraft on top of this layer of gas, which is now superheated, but it's still floating under the layer of the gas. So if you take water, you put it in a pan that's not quite hot enough, it just boils away instantly. You heat it up more, it stays there longer. It's got this cushioning layer of gas that's protecting that little droplet from doing anything. Same thing works in reverse too. I put something hot in there, it gets a protective layer of gas. So that's what's happening right now. That's why it's boiling like mad wherever it touches it. That piece of copper is being protected by the leading frost effect from cooling down. So it's going to take a while for all that heat to conduct in.